Welcome to properties of unit tests. There has been a change of schedule, so if you came here for the core guidelines, then you're in the right room, but 90 minutes too late, so sorry for that one. So this is a stand-in talk for one of the people that could not make it today. So let's talk about unit tests. I'm Arne Mertz. I work at Zühlke Engineering. Please ignore the Twitter handle. That's old times. I work mostly in embedded software, sometimes different projects where we have other stuff to do. Learning C++ for almost 2 decades because I don't think you ever stop learning. At least I don't. And I train usually people in our company, sometimes outside the company, and C++, maintainable code, clean code, refactoring, this kind of stuff. Let's talk about unit tests. If you look up definitions of unit tests in the web, there are dozens. So instead of inventing yet another or citing 1 or 2 or 10 of them, I just made a word cloud. Of course, I talk about unit and about tests, about software. If you squint a bit, you see individual, module, component, smallest, function, developer, and so on. A few of those common themes I will point out. Usually all these definitions say unit tests are automated tests written by the programmer. So not by a specific tester, not doing manually, automated tests written by us, basically. Written by us also means usually in the same language that we write our software in. So in our case, C++. They cover the entire software. So test coverage of up to 100% should be goal. And we test individual units, whatever a unit may be. A unit is a small individual logically separated piece of code. That may be a single function, that may be a single class, that may be a small group of class, depending on how fine you can go to actually pick a single thing and test it. For example, if you wanted to test a standard vector or one of the other standard containers, you could not do that without also using and testing the associated iterators, right? And vice versa, you can't test the iterators without having the container. So in that case, the unit would be probably the container and the iterator and maybe whatever inner helper classes they use. You find quite often also on the webs a testing pyramid. They agree on the base, the broad one is a unit test. They're small, they cover everything. Then the next level, a bit more general, maybe not as much coverage, are integration tests. Usually you take multiple units, test how they interact together, maybe test how they interact with the surrounding system, operating system calls, multi-threading, file reading, stuff like that. Usually goes in integration tests, and then it gets a bit more fuzzy, depends a lot on the system. So if you have like a whole program, then it's a complete system test, or if you have multiple programs that you tie together to one system, then maybe you have subsystem tests, maybe you have acceptance tests, quite often written in different languages. So there are languages that use like Cucumber, Gherkin style stuff with Python scripted is something that I see quite often in projects. UI tests where you have like however configured test runners that click the UI for you to actually test what's going on and stuff like that. But the unit test, integration tests are usually then written in our case in C++. And the unit tests in below are the ones we want to talk about today. I will mention integration tests from time to time. So, but all the above, the UI tests and so on, is right now of no interest. So what do we use unit tests for? So they are a tool. What are they the tool for? For QA, quality assurance, they ensure that our units do the thing what we designed them for to do. They document failures. When a unit test fails, it hopefully just doesn't just say nope. It just hopefully gives us a bit of an error message what actually went wrong, right? We use them for test-driven development. For those who have not heard the term yet, who are not quite familiar with it, you start by writing a test case for a bit of the features that you want to implement. You start by writing maybe a bit of code so the test fails. In the beginning, it might not even compile. And then you start to write the code to actually make this one test pass. There's a bit of a refactoring after this, and then you start with the next test, usually in very small cycles. Depending on the literature you read, 30 seconds to 2 minutes. When it comes to larger projects in C++, that's usually how long it takes to actually compile this stuff and then run the tests. Well, then you pass the 2-minute marks. And most projects I try to aim, when I actually do this, going for 5 to 10-ish minutes. But that also says something about that probably our unit test should not run 20 minutes because then you're out of the cycle, right? Unit tests are used for fixing bugs. When we find a bug and we see that is a error in the specification that we haven't called yet for our specific unit, then we write a new test to actually make sure that this part of the specification is actually adhered to, and then we change our code to actually match the test and be green again. For that, so they confirm correctness, and for that we also have to select specific test cases because we don't want to run our whole unit test suite just because we want to test this one test case, right? They're used for refactoring. If I change my code without changing the functionality, which is refactoring, maybe to make it more readable, maybe in some cases to structure it better, maybe even to change part of the performance, then I want to preserve the correctness of the code, right? I don't want to be afraid to break anything. So unit tests give me confidence that I actually still have correct code and I did not just mess it up completely. And to actually do this, I need short feedback loops because I don't want to program for a day or 2 days and then find out that somewhere in between I messed something up and now I start a 2-day debugging session to actually find out where the problem is. And we can use unit tests for documentation. We can, if we write them well enough to be readable enough, then unit tests show us how the author of the unit and of the test case has designed our class, our function to actually be used. If we have no other examples of how to use our class, then the unit tests of the class show us this works. This is how you can use this class to actually give correct code. And for that to work, those tests should be somewhere co-located with our code. It makes no sense to have like our repository with the code here and a different repository with the unit test there, because then good luck matching the two up, right? So from these use cases, what are the properties that we would like to see, like to have in our unit tests? A little of a disclaimer. These are not rules. These are not even guidelines, if you were in the last talk. These are suggestions. They have turned out to be quite useful. Much of what I talk about here, I came up with it myself, so it's like collection of experience, collection of what I've heard other people talk about that work with unit tests. So this is a bit proven, but everybody has their own surroundings. So as I said, no rules. Especially be pragmatic. There's no use in eking out the last bit of readability in your test cases if it takes you weeks, right? So there's also other stuff you have to do. But trying to make our unit test, for example, documentation is usually a good thing. Most important part, however, about tests is the correctness part. They should prevent bugs, and they should improve our confidence in we can change code without actually by accident breaking something that we don't think about right now. To have correct tests, we should not reproduce our logic that we have in our software. If I test my function by comparing it with the very same algorithm, just duplicating the algorithm with a different name in the unit test, then I test the algorithm with itself. When it has a bug, well, then I have the same bug in my test code and I never find it out. So what do we want to do instead? We don't want to have complex logic in our tests, because the more complex our logic is, the more likely is it that we actually introduce bugs in the test. We write the test to test complex logic, right? Who writes the test to test the test? An easy way is, or a common way is, to input and expect constants. I have a set of input that I know, and I have to figure out what the expected output should be for this. And if I have enough cases of inputs and outputs, then I can be pretty confident that for all the millions of other cases that I could have as input, I will get the correct output as well. This improves maintainability because I can read the code from top to bottom and not have like, okay, what is this complicated logic that I have to go through? And it avoids, as I said, the bugs that I have in the complex logic. Maybe even I have different complex logic to test my code than the logic of the code, and then the test just tells me, yeah, well, this piece of complex logic does not match this piece of complex logic. Good luck figuring out which of the one is the correct one, right? We want to do gray box testing, meaning we want to test not against the implementation details in our code that we test. We want to test against the interface. So when we have a class, our unit tests should not be friends of our classes. They should not know what's in the class, what the private implementation details are. They should get our external interface, call the functions they need to call, and then see that the observable behavior of our class or function or whatever is what we expect it to be. Because that's how it is used in our code base anyway, right? The observable behavior is the part that we are interested in. However, it's not black box testing, it's gray box testing. We want to use our knowledge about the inner parts to find edge cases. Think, for example, you have a container, string, whatever, that has a small memory optimization. A string that, when it's less than 10 characters, has the characters in an internal buffer inside the string, and if it's more, it actually allocates memory and allocates the memory externally. Then you want to write a test case for 10 characters, see that it works, and one for 11 characters across the border to the allocation, see that that one works too. Because you want to have like these two cases, internal memory, external memory, I want them tested, right? And then of course also other edge cases, how does my container behave when there is 0 elements inside it? Does it really work? And stuff like that. So a bit of implementation detail knowledge is needed to actually know what cases to trigger, but still test against the visible, usable interface. To prove that our code is correct, we want to have good code coverage. As I said in the beginning, up to 100%. In most cases, when the code base is sufficiently complex, you won't get to 100%. And it's, even if you could get to 100%, it's usually not feasible to do the 100%. You can't usually test your main function anyway, at least not in a unit test. It's really hard to call the main function, right? And there are other parts where, like, don't try to simulate a network error or something like that when it's really hard to do so, or some physical surroundings that are needed to actually trigger something. But if you have to basically guard against this kind of stuff, then you will have your error handling cases that you just can't unit test. And that can be okay. This should be little cases, small cases that you can say, okay, on inspection, we have a good confidence that these error handling cases and similar stuff works. The rest I would like to have unit tested. We can use strong domain types, which can lead to focus tests. Let's say we work with addresses. A street number is not a string, because hash bang add question mark is not a valid street name, right? So we have constraints to our street names. And when we introduce a type street name that may just wrap a string and have some checks on construction, then we can write unit tests to actually see, okay, does this constructor accept the correct strings and reject the wrong strings? And then we never have to check about, worry about these things again. We don't have to check whether our code that works with street names works well when the street name is an empty street name, an empty string, because our street name is not an empty string. That's not possible. So if we constrain our types, our domain logic, to what is a valid example and what is not, to specific types, then we can test those types and then just use them in our unit test without having to check those constraints over and over again. About readability. With readable test code, it's easier to understand failures, because we can go through the test code and see what's the problem. Readable code makes better documentation for the use cases of our classes. Readable code makes better maintenance. So all these clean code principles, readable code principles, and so on that you hopefully use in production code, you also want to use in test code. You don't want to copy paste your test cases from and have like 200 lines of test case, again 200 lines of test case and only 20 lines are different or something like that. Meaning we want to use design principles. We want to have meaningful names in our test case. Because, well, as I said in the beginning, the answer nope is not a good answer. But the answer test case 2476 also is not a good error message, right? So write what does this test case test, and then you see in your log output pushback on a vector does not increase the size. Okay, that's the problem, then I will know where to look, right? Use abstractions, test fixtures, helper functions that make your test shorter, because you don't want to have like 50 lines of test setup and then your actual test case, the interesting part starts. You want to call your common test setup function or the constructor of your test fixture runs, and in the test case you immediately see the interesting part. This makes test cases shorter so we can just read through them. To make test cases short in unit tests, we want to have one fact per test case. If I test 20 different things in my unit test case and it fails, then I know one of 20 different things is going wrong, but I don't know what exactly is going wrong. If my test case for the default constructor fails, and I see that, then I see something is wrong with the default constructor. When the test case, only the test cases that use pushback or something like that fail, then I know something is wrong with pushback. If I have a test case that uses all the functions at once, something is wrong with my vector, but I have no idea what. Test cases should also focus on the unit under test, meaning I want to test this class or these 2, 3 classes that belong together that form a unit. I don't want to test the other classes that I have to use to actually use this unit. When I test my address book, I don't want to test that my street name constructor actually works. I have tests for the street name class, right? So when those don't fail, then tests in my address book test cases should hint to a problem in the address book and not in the address. Especially, please don't test that your compiler works. I have seen tests that just check that copy constructors generated by the compiler actually copy things from A to B. If that is a problem, then you have a much bigger problem. Then your compiler is broken and you can just go home. Writing readable test cases are also a usability check. If you can't write a test case that gives a nice presentation on how to use your class, then probably it's also not easy to actually use your class in production, right? How do we order test cases? Well, people usually, when they read, they like to read from top to bottom. So we start with simple stuff. Does the default constructor work? Do simple things work? And then to the bottom where the more complex things are. So try to order your test cases in a way that actually make them one readable documentation. If I know nothing about the class and I read all the test cases from top to bottom, then they should be more or less like a documentation story that tell me from start to finish what I need to know about my class, and I don't have to jump from, okay, where are the constructors? They're way down there. I have to read them, and maybe then I can read the first test case that is about some convoluted function, order them in a way that makes them top to bottom readable. How can I discover my test cases? I know I have a new class or a class that I have to work with. How do I find the test cases for the class? Maybe to read the documentation that I have in those tests. This is usually done by convention. If we have a class XY, then you probably have an XY test and not some complete different name. Whether it's XY test or test XY, I don't really care. As long as all your tests have the same naming convention in relation to the class or unit they test as the others. So either all start with test or all end with test or something in that area, but not like a complete mix. This goes for the test files, of course, as well. This goes for test directories. Where do I find those tests? They're completely different conventions. Some projects have relatively little CPP files in one directory and just put the test CPPs in the same directory. Some put a test directory in the directory and all the tests for my directory are in the test subdirectory. Others say, okay, this is my source structure, my source directory structure. And besides src, I have a test directory. And the whole directory tree that I have here is reproduced here. So I have basically the same. When I have my file under source something, something, something else, then I have my test under source something, something, something else to just be able to navigate this. All can be valid. It's up to you to come up as long as it's consistent. I mentioned the 25-minute test runs, right? We want to have speed in order to have short feedback loop, in order to know early when we broke something, in order to be able to work just a bit, see was this a problem, continue, was this a problem? Because the faster we can run our tests, the faster we know when we have broken something. And when all goes astray, then I know I broke something in the last 5 minutes. I have no idea what. Okay, I roll back for 5 minutes, try something else. No biggie. If I know I broke something I did in the last week, if I roll back to last Monday and tell that in the daily, then maybe my boss laughs at me funny, because I start over from where I was a week ago. So I invest another week to actually find the bug, and maybe that's not good either. So working in small increments and testing in between to make sure that I did not break anything that I can discover with the unit test usually is preferable, but that means we want to have really, really fast tests. A very rough back of the napkin estimate. Let's assume that on a very productive day, we touch code that affects around 1,000 to 10,000 lines of code. Does not mean we write 10,000 lines of code in a day. No, maybe 50 or 80 or 100. But the code that is effective, this order of magnitude. Roughly, test code to production code, 1-to-1. Usually from experience, I would say more 10-to-1. So 10 times as much test code as production code, depending on how much confidence you want to have in your code, right? If you do regulated stuff, medical stuff, maybe it's more like 20 or 50-to-1, but depends. So if we use these, then it means 10 lines of code per test case that we want to have one readable test case. That means for those 1 to 10,000 lines of code that we affect, we have to run 100 to 1,000 test cases, roughly. Factor 10 is, if we want to have a feedback cycle in minutes, 5 to 10 minutes or something like that, that means our test should run in seconds, because I don't want to type for 30 seconds and then run tests for 9 minutes, right? If I want to have about 1,000 tests run in seconds, that means our test case runtime per test case should be milliseconds. That restricts what we can do inside one test case. If you read a couple gigabytes of data from a file, then we easily go past a few milliseconds, right? That means we want to decouple our code that we test in unit test cases from slow code. Usually, broadly speaking, this means separate infrastructure code from tests and from production code. This implies we may have infrastructure code in a separate library or something like that, put aside, tested separately. This kind of infrastructure code, usually, unless you are in the business of writing infrastructure stuff, usually doesn't change that often anyway. So if my stuff that accesses files or that accesses database connections or that sends packages over the network does not change, I don't have to run it every 2 minutes. And if I pull that code out of the test cases, out of the units that I actually test, then I don't have to compile and run it with my tests. That means we want to test the domain logic, the stuff that we actually care about, that stuff that we are actually developing. And the infrastructure code can be tested together with the domain code in unit tests, in integration tests, sorry. Integration tests are fewer. We probably don't run them every 5 minutes, so we can have longer running test cases that actually get proper data from a file or via a network or something like that, and see that our tests, code runs with them correctly. While in our unit test, maybe we just want to inject, per dependency injection, a mock network or a mock file that just sends some data from memory that we know about, that we define in our test cases, constants, and then we let it work with that one. It also means we should keep our code simple. And YAGNI means you ain't gonna need it. Don't write generic code when you don't need it. If you, let's say very simple, we have 2 numbers that we have to add, then our function should add 2 numbers. And we don't want to have a generic function that takes template parameters, maybe numbers, maybe something else, and takes a very related template. It can be any number of arguments. So instead of only testing for 2 numbers, I also have to test for what is when I add 20 strings together. That's not a use case in my program, but I have to test it anyway to prove that this template contraption is correct, right? So keep it simple. Don't write generic code where you don't need generic code. We want our tests to be independent from each other. When we are tracking down a bug or something like that, we want to run that one test case that fails, right? We don't want to have to run the other 2,000 test cases that we usually run before to actually have in some global state the same state that we usually have when we run this test case. I've had it that we had code that heavily relied on singletons and global state, and we could not run our test cases individually. We had to run most of our test cases in a very specific order to have the global state in a specific way that was expected by this one test case. That was one of the reasons why we needed 25 minutes to actually test this stuff, because we needed to run 5,000 test cases or something like that. So we want to test individual units. We want to decouple our units from dependencies, usually using dependency injection and similar methods. And we want to be able to repeat those individual test cases. That means we want to be able to filter our tests. Goes again to naming, maybe tagging our test cases. So anything that is related to a specific subsystem or something like that gets a tag, my fine subsystem, and then I can run all the tests that have this tag, and I get just a subset of my test cases executed. Because when I have a very large code base, millions of lines of code, then there will be tens of thousands of test cases. Or when we say this 1 to 10, there will be hundreds of thousands of test cases. We don't need to run them all. We only need to run those test cases that actually affect the code we are right now working on, right? If I work something in the UI, then I don't need to run my database tests every time. Tests should be repeatable. They should be deterministic. The biggest enemy of determinism and also timing is multithreading. You never know what the scheduler does, which threads and which parts of which thread gets executed in which actual order. So unit testing multi-threaded stuff is really hard. And also starting threads is in general a system call that takes a couple of microseconds, and when we do that too often, we lose too much time. So probably we want to have the single-threaded parts to test and then leave the multi-threading to integration tests again. Timing is also hard. Sometimes you have timing constraints. Testing that can be hard. When I have a test case that says, well, when I send this message, then I expect a response inside of 500 milliseconds. And I tie all this to my system clock, then I have to wait for 500 milliseconds to actually see whether the test is broken or not. And when I talked about a test case should take time in order of milliseconds, I mean single or double digit, not 500. And when my test case says 2 seconds, then I'm way out of the couple milliseconds, right? So what can be done, for example, is externalizing the clock. So the unit does not directly call my system clock, but it calls a clock interface, and I inject a clock. In production, that will be the system clock. In unit test, that will just be a clock interface, where I say, and well, by the way, right in the next line, the 2 seconds have passed. What do you do now? Right? So we can basically run the clock faster in our unit tests. As I said, we want to avoid global state, which gets transferred between tests, which also is hard to reason about, because we cannot just look at our code and say, okay, I know exactly what value is in this global variable over there. And this includes global state inside test cases. I've seen that kind of stuff as well, like static variables in test case fixtures. Please don't. Dependency injection can help us to tailor outside state. For example, to specifically for a test case, define what my database would return in this case. So, as I said, all this database stuff, all this kind of stuff that gets queried inside our units, if we can inject that from the outside, then it's much easier to actually simulate an environment for our units that we test than to actually have to trigger the right calls to actually get to that environment in a normal way. Dependency injection also helps us to trace interactions. For example, if we have some logging class or something like that, then having the logging class write to I don't know where is harder to actually test what has a logging class written than when I just injected logger interface into my class and can just trace what calls did I get on my logger interface, what did the unit under test try to log here, or not only logging, but any kind of interaction with the outside world, right? I can even inject the correct logger wrapped by something that just traces, okay, this call came in, and I just give it to the actual class, to the actual logger. But I can use mocking frameworks and stuff like that to trace these interactions while still having the actual, maybe a bit more complex logic in the backend. And with that, I'm through in record time. I'm sorry for that one. Are there comments, questions?